Hello and welcome to microwave tube lecture series. In last lecture we have seen lead inductance and interelectrode capacitance effect, and we have obtained expression for input impedance of triode tube, and it is clear that real part of input impedance varies inversely with the square of the frequency and imaginary part varies with the third order of the frequency. So as if we increase the operating frequency, input impedance becomes small at a point over and above of 1 gigahertz. Input impedance can become a short so that output power reduces. That is why these conventional tubes cannot be used at high frequency. So how to reduce this effect of lead inductance and interelectrode capacitance is that lead length lead lead length can be shortened, or we can use leads of short lengths, or we can also reduce electrode area. So that will result into smaller capacitance because C is equal to epsilon A upon D, and reduction in length will reduce the lead inductance effect, and reduction in electrode area will reduce the interelectrode capacitance effect. But both these solutions will result into lesser power handling capacity for that particular tube. So these solutions will not be so useful to avoid the lead inductance and interelectrode capacitance effect. Now in today's lecture we will see the next limitation, which is transit angle effects, as well as we'll see gain bandwidth product limitation. So what is transit angle effect? So the second limitation of conventional vacuum tube is transit angle effects. Because of this effect, efficiency of vacuum tubes reduces. Because of transit angle effect, efficiency of vacuum tube reduces. So what is this transit angle effect? So for this, first we will try to understand transit time. So transit time is actually time required for electrons. If we consider the same circuit, triode, so the transit time is time required for electrons to reach to grid when they have started from cathode. So once they have reached to the grid, electrons will be quickly absorbed or attracted by the high positive potential plate. So that is why transit time is time required for electrons to reach grid when they have started from cathode. So because of this effect, what will happen if we consider two cases? One is low frequency case and one is high frequency case. So first I will write for transit time. So it is time required for electrons to reach grid when they have started from cathode. So it is denoted by tau g. So transit time is time required for electrons to reach grid when they have started from cathode, and it is denoted by tau g. G stands for gap. So time is distance upon velocity. So d is the separation between cathode and grid, and electrons will be traveling with some velocity v0. And if we convert this into angle, when we multiply by omega, so it would be omega tau g, that is theta g, called as a transit angle, is equal to omega d by v0, where tau g is what? Transit time across the gap. Theta g is transit angle. D is separation between cathode and grid. Separation between cathode and grid. And V0 is actually 0.593 into 10 to the power 6 under root V0 meter per second is the velocity of electrons. How we have calculated this? Under thermal equilibrium we can equate static and kinetic energy, so we'll get this. We'll do this in our subsequent videos. And finally, capital V0, which is here, is the DC voltage. So this is, we have discussed about transit time and transit angle. So what is this effect? What happens because of this effect, and why efficiency of vacuum tubes reduces because of this? So at low frequency, if you draw a low frequency signal, it will have higher time, something like this. So this is a low frequency signal, and let us assume you have transit time. It's some time, maybe a time of up to this point 10 millisecond. So up to this point, if you are operating at low frequency, phase of signal is not changing. So this is transit time. For example, we are assuming 10 millisecond is the transit time. For 10 millisecond, if you are operating at such low frequency where phase is not changing for this transit time, so electrons can start from cathode and they can go to the grid, and then they will be reached to the plate, so current will flow. So there is no problem at low frequency because of this transit time effect. Now let us assume you have increased operational frequency from very low value to very high value, let us say 1 gigahertz, 2 gigahertz, and so on. So because of high frequency, now the time would be less. So something like this we have. Time period would be very small. Again, transit time would be same. We are not changing the transit time, but we have just increased the operating frequency. So because of this, now you can understand it is the time required for electrons to reach grid when they have started from cathode. But in between, because of high frequency, the signal is changing its phase several times from positive to negative, negative to positive, positive to negative. So the energy electrons acquired during negative cycle will be released during positive cycle. and it may happens maybe 10 to 100 times in between this particular transit time. So because of field is changing from positive to negative and negative to positive, so during negative half cycle energy will be removed, and during positive half cycle electrons will get the energy again that will be removed during negative half cycle, again they will get during positive half cycle. So because of electrons getting energy and the same energy is being released during negative half cycle, so considering this circuit, electrons getting energy, releasing their energy, again during next cycle they will be getting energy, so they oscillate forth and back between this particular region. So let us make it very clear. During positive half cycle electrons receive the energy, and during negative half cycle the same energy would be removed. Electrons energy will be removed. So because of this phenomena electrons will oscillate forth and back between the space cathode and grid. That is why it is said that they cannot reach grid, they cannot go to the plate, and current cannot flow through the tube. That is why it is said that efficiency of vacuum tube reduces because of the transit angle effect. So what is solution for this? So solution to avoid transit angle effect is that we could apply very high DC voltage which is V0, and then once you have given very high DC voltage then electrons can travel with very high velocity, and later on you can modulate their velocity, which is indeed the principle of operation of all microwave tubes. So this is about transit angle effect. Now the third and last effect which we have to discuss is gain bandwidth product limitation. So the third and final effect is gain bandwidth product limitation. So because of this effect, because of gain bandwidth product limitation, higher gain, so let me first give the title, third and last effect, gain bandwidth product limitation. So because of this effect, due to this, higher gain is achieved only at the expense of a narrower bandwidth. Narrower bandwidth. So the meaning of this is that if you have a frequency response of a tube, gain over a frequency, and if you have response something like this, if you wanted to increase the gain, you can always increase the gain, but you have to compromise for bandwidth. So gain would be increased, but bandwidth would be smaller. What is bandwidth? Whatever maximum value we have to take 3 dB down of that. So that is actual our bandwidth. So in this case, if you take 3 dB down and determine the bandwidth, so it is smaller as compared to earlier bandwidth, right? And if we try to improve the bandwidth, we have to compromise for gain. So that is the limitation of gain bandwidth product limitation. That means gain and bandwidth are inversely related. So we'll try to prove this, how gain and bandwidth are inversely related. For this particular limitation, we'll consider the output tune circuit of a pentode. It has GM VG is the current flowing, plate resistance RP, load resistance R, and tuning elements L and C, across which we are getting some output voltage. So what we do, we will try to obtain gain and bandwidth for this resonant circuit. So gain is what? Output voltage upon input voltage. So first we'll write for VL, which is the load voltage. So how I can write for VL? By looking at this circuit, VL is equal to V is equal to I into R. So what is current? Current is GM VG and R. So all this resistance, two resistances and two reactances are in parallel. So equivalent resistance, I could first write likewise, 1 over R equivalent is equal to 1 over R P plus 1 over R plus 1 over J omega L plus 1 over J omega C. So that is J omega C. Therefore R equivalent is 1 over of this quantity, and that is 1 over RP plus 1 over R plus 1 over J omega L plus J omega C. Now this is your R. Let us take it to the VL. So it is GM VG. R equivalent is 1 over RP plus 1 over R plus 1 over J omega L plus J omega C. Let us consider this term as some term G. Okay, so VL, which is a load voltage, is equal to GM VG divided by G plus, let us take J common from this, so it is omega C minus, if I have taken J common, I have to multiply and divide by J, so J would be outside, J into J square, it would become minus 1 over omega L. Okay, let us write where G is equal to 1 over RP plus 1 over R. RP is plate resistance, R is load resistance, L and C are tuning elements. L and C are tuning elements. So for gain, as we know that gain is, voltage gain is, let us say, output voltage VL upon input voltage VG. So above equation would become GM by G plus J omega C minus 1 over omega L. So this is gain, but we are interested to obtain for maximum gain. So maximum gain is only possible at the resonance. We know the equation for resonant frequency. Fr is equal to 1 over 2 pi under root LC, and at resonance frequency XL is equal to XC. At resonance XL is equal to XC. So from this equation, if you wanted to obtain maximum gain, so it is possible at resonance, and will be equal to, when these two quantities XL and XC are same, it would be cancelled out, so it is GM by G. Therefore A max is equal to GM by G. Now this is about maximum gain, and we have to talk something about now bandwidth. So as we have discussed at the start, how do we measure bandwidth? So if we have frequency versus gain, and graph is something like this, gain or output power. So whatever, let us say we have written output power. So if we have, let us say, 10 watt of output power, so while determining maximum output is 10 watt, while determining bandwidth for this curve, we take 3 dB down, or power would be half. So half power point we have to determine. So it is 5 watt on either side, and take projections on the frequency axis. So this would be the bandwidth for this graph. So why we take half power? Because the bandwidth definition says that from 100% or A max value, if you deteriorate up to 70.7%, that is acceptable. Up to that deterioration is acceptable. So that is the satisfactory range of frequencies over which any circuit can operate satisfactorily. So if it is, let us say, 10 volts, so in case of voltages, it would be, means while determining bandwidth, it would be 7.07 volts on either side. That is 70.7% of that. If it is milliamp currents, if it is current 10 milliampere, so again it is 7.07 milliampere on either side. If it is power, so it has to be half. If it is a dB signal, let us say you have a gain of 10 dB, so you have to take 3 dB down. So all these things meaning it's same. So to understand this, let us do a small exercise or a small case study. If you have a 10 watt of output power and trying to convert it into the decibels, so 10 log base to the 10 of 10, so this is your 10 watt, and half of that is 5, convert it into the decibels, so 10 log base to the 10 of 5. So solving this means converting this power into decibels, so it would become 3 dB. Similarly, if you have voltage, let us say 10 volt, so 70.7% of that is 7.07. Convert this into the decibel value. So while converting voltage or current, we multiply with 20 log base to the 10 of that voltage or current value, because dB is for applicable, means first time applied for power, and according to conversion from voltage power to voltages or current, square term will appear there, so that 2 will get multiplied with this 10, so it would become 20 log base to the 10 and 20 log base to the 7.07, which is 70.7%. so solving this, it will again give you 3 dB down. So voltages or current it is 70.7%, that is divide by root 2. If you have dB value, it is 3 dB down, and if you have power, it has to be half power. So all these things are saying the same story while determining bandwidth. So conclusion is that if you have power, take half of that. If you have dB, take 3 dB down. If you have voltages or current, take divide by root 2 for those values. So in this case, let us assume we have a power we have to determine at half power points. So A max, I will clearly write here. We know that bandwidth is measured at the half power point. Bandwidth is measured at the half power point. Therefore, the denominator, what is our denominator for this given equation? G. Denominator must be related by. So this term, if this term is related by G, so this would become Gm by 2G, so that is half of that. That is why we are relating G is equal to omega C minus 1 over omega L. So that is why half power point will get. Now this is a quadratic equation. This is a quadratic equation. Now let us solve this equation. So G is equal to omega square CL minus 1 by omega L, that is G omega L equal to omega square CL minus 1. Finally, omega square CL minus G omega L minus 1 equal to 0. So from this, A is equal to CL, B is equal to minus GL, and C is equal to minus 1. Now solve this quadratic equation using minus B plus or minus under root of B square minus 4AC by 2A. So is equal to, now let us put the value for A, B, C and solve it. Minus minus will become plus, so plus GL plus or minus under root of minus GL square will be G square L square. 4AC will be 4 minus, this C is minus, minus minus will become plus, so 4 A is CL and C is minus 1. That is why now we have the denominator 2, A is CL. So let us solve this. Let us take L common from numerator and denominator. G plus or minus under root of G square plus 4 C by L, divided by 2C. So L and L can be cancelled out. So G by 2C plus or minus, now let's take 2C to the numerator, so G by 2C square plus 4C by L divided by this 2C If it goes inside the square root, it would be 2c square. So 4c by L into 1 by 4c square. So what it would be remaining? 4 can be cancelled, 1c can be cancelled, so 1 by LC. So finally g by 2c plus or minus under root of g by 2c square plus 1 by LC. So the roots for this quadratic equation, we have omega 1 is equal to g by 2c minus under root of g by 2c square plus 1 by LC, and omega 2 is equal to g by 2c plus under root of g by 2c square plus 1 by LC. So bandwidth, we know that it is omega 2 minus omega 1, so is equal to g by 2c plus g by 2c. We are ignoring 1 by LC because this is very small quantity. G by 2c square is very larger than 1 by LC because it includes load resistance and plate resistance, and LC are the tuning elements. So this is omega 2 minus omega 1, g by 2c minus plus g by 2c. So this will be cancelled out. So bandwidth is equal to g by c. So now we have obtained equation for gain as well as bandwidth. Now let us see the product of gain and bandwidth is what. So if we take product of gain and bandwidth, so A max into bandwidth. So A max is Gm by G and bandwidth is G by C. So this can be cancelled out. So finally A max is equal to Gm by C. A max into bandwidth is equal to Gm by C. So if you take bandwidth to the right side, we have inverse relation between gain and bandwidth. So whenever we expect higher gain, we have to compromise for a bandwidth, and if we want higher bandwidth, we have to compromise for gain. So due to this, higher gain is achieved only at the expense of a narrower bandwidth. Now finally, since last two videos we are trying to understand the limitations of conventional vacuum tubes, so let us summarize them. Lead inductance and lead inductance and interelectrode capacitance effects. Then we have transit angle effect and gain bandwidth product limitation. So because of these three limitations, conventional vacuum tubes we cannot use at higher frequencies. Because of first limitation, output power reduces. Because of second limitation, we have seen that efficiency of the tube reduces, and because of third limitation, whenever we expect higher bandwidth, we have to compromise for gain. So the solution for gain bandwidth product limitation, rather, whenever we use resonant cavities, this limitation will be always there. But in case of microwave tubes such as two cavity, multi cavity, reflex, traveling wave tube and magnetron, we use the reentrant cavities. So therefore now we are ready to discuss microwave tubes. So in the next video we'll start with the first microwave tube. Thank you.